In this lesson, you will learn about the most common FortiSwitch topologies, as well as the different loop prevention protocols and methods available on FortiSwitch. In this lesson, you will learn about the topics shown on this slide. After completing this section, you should be able to achieve the objectives shown on this slide. By demonstrating competence in Spanning Tree Protocol, STP, you will understand the fundamentals of loop prevention in Ethernet networks. To build resilient networks, network administrators often deploy additional links between switches to ensure that traffic continues to flow if one of the links fails. However, if no loop prevention method exists, the multiple links may create a Layer 2 loop that results in broadcast storms and MAC address table instability. Unlike IP packets, Ethernet frames do not have a time to live (TTL) attribute. This means that Ethernet frames disappear from the network only when they reach an endpoint or are dropped by a switch. A switch forwards broadcast and multicast frames to all its ports, except the port where the frame was received. If there is more than one active path between adjacent switches, the same broadcast and multicast frames initially forwarded by the switch are eventually received on the same switch, but on a different port. This results in the switch forwarding the same frames repeatedly. The traffic increases with every new broadcast and multicast frame sent by endpoints, which eventually leads to insufficient network resources to forward user traffic. MAC address table instability is a result of broadcast storms and occurs when a switch learns a MAC address on a port that is different from the port on which the MAC address was learned previously. This is also known as MAC address flapping. The result is that the switch must update the MAC address table with the most recent port where the MAC address was learned. Because in a broadcast storm, the same broadcast and multicast frames are exchanged back and forth on different switch ports, the switches must update their MAC address tables after each exchange, which results in more CPU activity. The CPU usage becomes higher as the broadcast and multicast traffic grows. The increased CPU utilization may then slow down network traffic processing tasks performed by the switch, or even prevent them from running at all. The example on this slide depicts a simplified Layer 2 loop. When the PC sends a broadcast or multicast frame to switch 1, the switch forwards it to switch 2, and this to switch 3, and so on. When switch 1 receives the frame from switch 4, it forwards it again to switch 2, starting the loop. Switch 1 must then update its MAC address table because the MAC address of the PC has now been learned on the port that connects to switch 4. STP, which is defined in IEEE 802.1d, is a Layer 2 protocol that enables Ethernet networks to build loop-free logical topologies. Switches that run STP exchange Bridge Protocol Data Units (BPDU) that contain information about the network topology. The switches then use the information in BPDUs to determine the root bridge and the cost of all links to the root bridge. The switch then enables the best link, cheapest, to the root bridge and disables all other more expensive links. The network achieves STP convergence after all switches determine the root bridge and the best link to it. Because STP disables the alternate links, the network becomes loop-free. The switch with the lowest bridge ID is elected as the root bridge. The link with the lowest accumulated path cost to the root bridge is selected as the best link. The cost of a link is inversely proportional to its bandwidth. That is, the higher the bandwidth, the lower the cost, and vice versa. A network STP reconvergence is triggered when switches detect a switch with a lower bridge ID than the current root bridge. This results in a new root bridge election and therefore, in the recalculation of the best link to the new root bridge. When the best link to the root bridge fails, the switch ports for the alternate links go through a series of STP states to determine the new best link. Ultimately, the switch enables the new best link to the root bridge and disables all other links. The example on this slide shows 4 interconnected switches running STP and the cost of each link. Switch 1 was elected as the root bridge. Therefore, the other 3 switches must build a loop-free topology towards the root bridge. The result is that STP disables the link between switch 3 and switch 4 to prevent a loop. The first step for STP convergence is to determine the root bridge. The switch with the lowest bridge ID is elected as the root bridge. A switch includes its bridge ID in its BPDUs. When switches are powered on, they send BPDUs to the network and initially announce themselves as the root bridge. Later, if a switch receives a BPDU that contains a lower bridge ID, the switch stops advertising itself as the root bridge and instead relays the lower bridge ID to its neighbors. The process repeats itself on every switch in the network and ends when all switches advertise the same root bridge ID. The bridge ID is the concatenation of the bridge priority and the switch MAC address. You can configure the bridge priority, but not the switch MAC address. This means that you can influence the root bridge election by adjusting the bridge priority. On 40 switch, the default bridge priority is 32,768. You can look up the switch MAC address by running the get system status command on the 40 switch CLI, and then looking at the burn-in MAC line in the output. When comparing two bridge IDs, the switch first compares the bridge priority. If the bridge priority is the same, the switch uses the switch MAC address as the tiebreaker. That is, the bridge ID with the lowest MAC address wins. In the example shown on this slide, switch 3 has the highest bridge priority number, which automatically discards it as the root bridge. The other three switches have the same bridge priority, so their MAC addresses are used as the tiebreaker. When comparing the MAC address of each switch, switch 1 has the lowest MAC address, and for that reason, switch 1 is elected as the root bridge in the network. The second step for STP convergence is to determine the best path to the root bridge. The link with the lowest accumulated cost to the root bridge becomes the best root path. A switch includes its root path cost in its BPDUs. The root path cost of a sender switch is the sum of the costs of each link that connects that switch to the root bridge. When an adjacent switch receives the BPDU, it adds the cost of the local link where the BPDU was received. The receiving switch then advertises its new root path cost to its neighbors. When there is more than one link with the same cost to the root bridge, the switch uses the following tiebreakers to determine the best root path. Lowest sender bridge ID, used when multiple upstream switches have the same root path cost. The lowest bridge ID wins. Lowest sender port ID, used when multiple equal cost upstream links that are not part of a link aggregation group, LAG, connect to the same switch. The lowest port ID wins. The port ID is the concatenation of the port priority and the interface number. You can configure the port priority and cost, but not the interface number. This means that you can influence the best root path selection by adjusting the priority and cost on ports. On 40 switch, the default port priority is 128. The default port cost depends on the port speed. The higher the speed, the lower the cost, and the lower the speed, the higher the cost. The example on this slide shows 4 interconnected switches, the ports in use, and the port costs and priorities configured on each switch. The port that connects to the best root path is called the root port. The root bridge is switch 1 because it has the lowest bridge ID. As a result, the other switches must identify the port that connects to the best path to switch 1, that is to say, the root port. Switch 2, the path with the lowest cost to the root bridge is through port 1 and port 2. Both ports are connected to the same switch, switch 1, so STP uses the sender port ID as the tiebreaker. Both port IDs on switch 1 have the same priority, so the port with the lowest interface ID wins, which is port 1. Port 1 on switch 1 is connected to port 1 on switch 2, so port 1 on switch 2 becomes the root port. Switch 3, even though the switch has a direct link to switch 1, the path with the lowest accumulated cost to the root bridge is through port 1. For this reason, port 1 becomes the root port. Switch 4, it has 2 equal cost links to the root. STP uses the sender port ID as the tiebreaker. Port 2 becomes the root port because it is connected to port 5 on switch 1, which has the lowest port priority. The cost of a link is the same as the cost of the port connecting that link. In this course, link cost and port cost are used interchangeably. The higher the port speed, the lower its cost. You can configure the cost of a port on the FortiSwitch CLI. But in case you don't, FortiSwitch uses the formula defined in Rapid Spanning Tree Protocol, RSTP, IEEE 802.1w, to calculate the default cost of ports. Port cost equals 20 terabits per second divided by interface speed. You will learn more about RSTP in this lesson. The table on this slide shows the default port costs calculated by FortiSwitch based on the port speed. Note that the costs are for individual physical ports. When you bundle multiple ports together to form a lag, a new logical interface with a higher bandwidth is created, and as a result, the new interface has a lower cost than its individual members. For example, if you form a lag with two 100 gigabits per second ports, the default STP port cost for that lag will be 100 because the lag speed becomes 200 gigabits per second. When you connect a switch or endpoint to the network, STP transitions the impacted ports through different states before the port is placed in the forwarding state. The following are the different STP port states. Disabled, the port is down and is not part of the STP calculation. Blocking, the port receives BPDUs but does not send any. The port does not forward traffic. Listening, the port receives and sends BPDUs but does not forward traffic. Learning, the port receives and sends BPDUs, populates its MAC address table, but does not forward traffic. Forwarding, the port is fully operational. It forwards traffic, receives and sends BPDUs, and populates its MAC address table. During STP convergence, the port is assigned a role and placed in the forwarding or blocking state. The following are the different STP port roles. Route, the port that connects the switch to the best route path. A switch has only one route port. Designated, a non-route port that forwards traffic. All ports in the route bridge are designated ports. If one end of a link is a route port, the other end is a designated port. When the other end of the link is another designated port candidate, the port on the link with the best route path cost becomes the designated port and the other the blocked port. Blocked, a port that connects to an alternate path to the route bridge. The port is in the blocking state to prevent loops. A non-route bridge switch can have multiple blocked ports. On an alternate link, there is one blocked port only, which means that the other end of a blocked port must be in the forwarding state. The example on this slide indicates the roles of all the ports in the topology. In this lesson, you will also learn how the route port on each switch is determined based on the STP best route path calculation. The roles of the non-route ports in the topology are determined as follows. Switch 1. The switch is the route bridge, so all its ports are designated ports. Switch 2. The roles are as follows. Port 2. The switch already has a route port, port 1, so the port must be either a designated port or a blocked port. The port can't be a designated port because that would result in a loop. Therefore, the port is a blocked port. Port 3. The other end of the link is a route port, so the port is a designated port. Now, you will learn about the roles of the non-route ports on switch 3 and switch 4. Port 2 on switch 3 and port 1 on switch 4 represent the same case as in port 2 on switch 2. That is, they must become blocked ports to avoid a loop in the network. However, for the ports connecting the link between switch 3 and switch 4, you must identify which end of the link becomes the designated port and which one becomes the blocked port. This is because the other end of a blocked port must be a designated port. For this reason, you must use this tiebreaker to identify the designated port on the segment. On a segment, the designated port is the non-route port with the best route path cost. When comparing the route path cost from switch 4 to switch 1, which is 1, with the route path cost from switch 3 to switch 1, which is 2, the best route path is the one through switch 4. For this reason, port 3 on switch 4 becomes the designated port, and port 3 on switch 3 becomes the blocked port. If the route path cost for both switches is the same additional tiebreakers used in the route bridge election are used for the designation port. Lowest sender bridge ID, used when multiple upstream switches have the same route path cost. The lowest bridge ID wins. Lowest sender port ID, used when multiple equal cost upstream links that are not part of a leg connect to the same switch. The lowest port ID wins. The STP timers impact how fast STP responds to topology changes. The route bridge sends BPDUs at the interval defined in the hello timer, which is 2 seconds by default. The non-route bridges then relay the BPDUs down the spanning tree network. When a non-route bridge receives a BPDU, the configuration information contained in the BPDU is valid only for the time defined as the max age timer, which is 20 seconds by default. If a switch stops receiving BPDUs on a port for a period longer than the max age timer, the switch assumes that there has been a topology change and moves the port to the listening state first, then to the learning state, and finally to the forwarding state. The time a port stays in the listening state and in the learning state before moving to the next state is defined by the forward delay timer, which is 15 seconds by default. If a switch is using the default STP timer values, then STP may take up to 50 seconds to respond to a topology change, a waiting time that is considered extremely high in modern networks. Rapid Spanning Tree Protocol, RSTP, which is defined in IEEE 802.1w, was designed to provide significantly faster convergence than STP, while still being backward compatible with STP. Good job! You now understand STP. Now, you will learn about Rapid Spanning Tree Protocol, RTSP.